So it's our pleasure to have Professor Edgar Hertwich as our today's speaker. So Edgar is International Chair in the Industry Ecology at the Norwegian University of Science and Technology. So he also serves as a member of the International Resource Panel and the European Scientific Advisory Board on Climate Change. His work addresses footprint analysis, factor trade, technology assessment, and sustainable development. So his talk today is using the hypothetical extraction method to understand the role of materials and manufacturing. So the presentation will be about 30 minutes, and we'll follow up with the Q&A session for 15 to 20 minutes. So Edgar, thank you very much again, and the floor is yours. Thank you.
Thank you, Dr. Kwei-Sheng Feng. It is a big honor to follow all the esteemed colleagues who have spoken before me, and I'm glad to be able to present my work to the International Input-Output Association. I started this work with a practical question. We wanted to understand how important the production of materials was as a cause of greenhouse gas emissions on the planet. And we started looking at life cycle assessment data and input-output data and data from the International Energy Agency. And I sort of found that really there wasn't any good overview publications. And so that's when I initiated this work. And it was, of course, only the first step in work we did to investigate how these emissions could be reduced. But here I would like to focus on the quantification of the size of the emissions. And in some sense, I divide the talk between the theory or the methods of the work and the results. In the end, I also present some results from a recent paper that was published just 2 weeks ago, looking at the decomposition analysis of the carbon footprints of metals, so not all of the materials, and I will show you some results there. And so this is how I like to explain my students in industrial ecology how to look at the economy that consists of industries, so entities that produce products, using inputs of production factors on the left and intermediate products from below, and producing products that are then distributed by markets to final consumers and other industries. And the single line here indicates a vector. So here we have one dimension, and 2 lines indicates a matrix where we have 2 dimensions, products and sectors, if you want. And so I think this is important because if you isolate these 2 entities, industries and markets, you can make a balance around the commodity markets, and you get the market balance, and from that you can derive the normal Leontief demand pull equation. But you can also have a system boundaries around the industries. And that's actually when you get these production recipes where we have the factor input and the commodity input to produce outputs. And we can derive the Leontief demand model here, where the prices are given, describing the prices as a relationship of the factor inputs and the factor prices and the Leontief inverse. And implicit in this model is that we price the commodities that industries are using with the same price, so P times A, with the same price as we price the outputs. And in the end, if we replace the production factors of labor and capital with the labor, with the energy and other inputs that we have, we get a similar equation. We get multipliers for these environmental inputs or outputs that we produce, unwanted outputs costs that we impose on the environment in the sense per unit product produced. And I will show you why this is relevant. So this is the paper that was published 2 years ago. And if this is the A table, so the coefficient matrix of industry interactions, we can see here there are some industries that are of interest to us. In my case, they produce materials and the inputs they require of other goods and of production factors. And then we also, and they have markets, right? So the industries that demand those products. And of course, some of the materials are used to produce other materials, either directly or indirectly, because machinery was produced from them that is used to produce those materials. And so the question is, what's the net demand of materials, and how can we determine the quantity of materials that is needed by the rest of the economy outside the materials production industries? And this is where the hypothetical extraction method can be used. And in that method, what actually happens is that we extract, so we remove some of these numbers in the input-output table. In this case, I've removed the demand for materials, both the intermediate demand and final demand for materials. And you could also remove the production. That doesn't really make a difference, because if you calculate the production volumes, once you have removed the demand, of course, the production of materials is zero, right? And so the idea is that once you have removed these unwanted elements, you calculate a new x, which will be smaller. And this new x, the production volume, will indicate the amount of production that is necessary for everything apart from the materials. So by implication, it is assumed that the rest of the production was for the production of materials. And of course, then if you multiply this with the intensities or emissions per unit output of the different industries, you get the environmental impacts, which I was looking for. And the question is, how can it be, right? So what's going on here? And so some people have suggested that we could look at hypothetical extraction, like importing these things that we no longer produce ourselves from a different economy that is identical to ours. And then we have here as A naught, indicated as A naught, just the rows that contain the coefficients that we have removed from the table above. So that if you add up those two tables, A star and A naught, you would still get back the old coefficient matrix. And you do the same thing with the y vector. So you have this identity here that it describes the relationship of the variables. And of course, the assumption is that the coefficients of factor inputs are unchanged. So T star and T naught are the same. I just label them so that we can trace what comes from which system. And so X naught is then the volume of production that is necessary to produce, in my case, the materials, right? And A naught times L star Y star is, so if we want to calculate the production volume as we did, X star above, that's the amount of intermediate demand that is necessary to produce these extracted products, the materials to satisfy the demand for the remaining production. And here is the derivation. And so, of course, we have the X star again, which I calculated before. If we plug this in, so here we have the multiplication of this L star Y star with A naught. This gives us the amount of material that is needed by other industries, and then Y naught is just the demand for materials by final demand. And so you can see that basically I get this equation from this import system. So if I look at this as if this was imported, then I get this equation that I have, well, the final demand for materials times the amount of materials needed per product commodity produced in the other economy, and L is then the inputs that are needed to produce materials. And here again, L times Y naught is the inputs to produce materials. And the quantity, I mean, the question is this really the same? And so if you want to show that there's a few steps of algebra needed, what you need is that you need to know that L times A or A times L is equal to L minus I. And then you basically can start here. You replace Y naught by Y minus Y star and A naught by A minus A star. And then you multiply these things out, and then you identify the A times L or L times A, and you replace those by L minus 1, or in this case, L star minus 1, and you find out that you can cross out some terms here, and you're basically left with this expression. So with this, I basically have shown that these are identical, and this means that yes, we can divide the economy into two parts. One part which produces the materials, and the other part which produces all the rest, right? And the way I look at it is that what the hypothetical extraction really does is that it is able to identify which part of the economy was actually used to produce the materials. So a commodity that is mostly used as an intermediate input by other industries, you can clearly identify what share of the total economy is used to produce those things. And that this basic and standard, and I think was understood before I started my work. And then I also found it interesting to look at the production balance, which is the inputs of individual sectors that are needed to produce things. And on the right-hand side here, we have the balance for the materials, basically the extracted goods, and it's just the normal Leontief price model that I've showed you before. And then on the right-hand side, we have the price of the other commodities, consists of the inputs of the other commodities that are required, plus the inputs of materials that are required, plus the inputs of production factors, right? And then I basically do the normal Leontief algebra, and I end up with the price of the products consisting of two parts. One of them refers to the materials, and one of them refers to the other inputs. And I find that actually quite insightful, because here I can basically say, well, they are really the total price or value added. The total price contributes of the value added by the materials upstream from the materials and the materials production and the value added in the rest of the economy. And by implication, again, I look at the carbon footprint or the other factor inputs, just like the inputs of value added. And so you can apply that also the same calculus to carbon or energy or land or whatever you are interested in. Cost of extracted inputs and costs of inputs from the remaining economy. And so I basically formulate a multiplier here, which is just the share of, or no, the part of the total, which is from the extracted product. So with that, I can go over and go to present my results. As I said before, there was an incomplete knowledge. The IEA keeps track of energy use and emissions in energy-intensive industries, including materials production, but they don't include all the inputs in the supply chain. There have been some LCAs that were scaled up from what is called unit process results in LCA, which is per kilogram materials to total production volumes. But those are bottom-up calculations, and they do not take into account changes in technology from year to year, for example. And so they cannot be used to trace developments over time. And so I thought that IO was the right method to use that. And here are now the first results. Greenhouse gas emissions in the production of materials. These are all the materials I have tracked here in brown. This is a log scale on the y-axis. And so in black, we have the global CO2 emissions, and we can see the slope of the materials is higher than the slope of CO2 emissions. Of course, in the log linear chart, the slope gives you the rate of growth in percent per year. And so you can see that emissions from materials production have increased faster than emissions, than global emissions as a total. We can see that the second largest here is iron and steel, followed by cement, lime and plaster. So this was all done with IIOA, where we have quite a lot of detail on different materials. I'm afraid that the rubber and plastic is hard to see now, but it's this light yellow color. And then there are a bunch of other materials that are less important for greenhouse gas emissions, but maybe interesting in their own right. And then I was asking, where do these emissions happen? A lot of them are in the material production step itself, so iron smelting and aluminum electrolysis and cement production, right? Then the energy supply to the different production processes, and mining was surprisingly little important if you took away the energy, and so. And the line here indicates the total emissions now here are not on the log scale, but on the linear scale. And you can see that this has more than doubled in this time period from 1995 to 2015. Here again, it's the composition of materials. And here it is the demand. So which sector is demanding these materials? And we can see that close to 50% of the demand for materials is from the construction sector. The second most important sector is machinery and equipment. Surprisingly, in my field, industrial ecology, nobody has done much research on machinery and equipment. Metal products is the third most important thing. Again, those are intermediate products mostly, right? So they are then used in construction, machinery and equipment, or transport equipment. And so you wonder what they are actually. So there is more need for more research. Transport equipment is like vehicles and things like that. Then we have electronics, and then we have some other products, right? Some demand in services, some final use. And one can look at more detail what exactly is contained of those. But I should say in IIOA construction is a single sector, so we cannot break this down. How important are houses compared to bridges and roads and railways? That would be nice to know, but we don't really have that information in IIOA. And then finally, who is causing the demand, or which type of demand causes materials, the use of materials? And here I have consumption and investment, so I separated that out. And consumption has increased substantially, but investment has increased a lot faster, right? And all the construction is here. Most of the construction is in the investment, so you can see that comes out really important. And as the categories before just indicate that the investment is quite important. Whereas here, actually, Public administration, health, and education is the largest sector of the economy, obviously has grown quite a lot. Real estate services. So these are then the end use sectors in which the material intensive products are being used that show up. And then I have split this up by regions as well. And of course, what is striking is the significant contribution by China, where a large share of the investments actually happen. But also on the consumption side, there has been a substantial increase, and that is significant. And then we see some of the other emerging economies, of course, also growing. And can compare production and consumption-oriented accounting, and there is a net trade, and so China becomes an important exporter, whereas the EU or Europe and North America are important importers. That means that these countries either import materials or they import products that are produced with the help of these materials. And there is I spent some time, so I did the calculations for the consumption-based accounting, endogenizing the investments with a method that Carl Södersten and Richard Wood and I have developed, and there basically we assume that capital is being used or is being replaced as it is being used by new capital. But you can also look at this more dynamically in a paper that Ran Wang and a number of authors have forthcoming in PNAS. You will see that such a dynamic accounting basically has historical emissions for past investments of capital that we're using today, and then investments, basically emissions today that are used to produce capital that is being accumulated or newly invested today. And this is basically what this picture tries to explain. So overall, we can see that materials are mostly used for capital equipment, and that's why capital equipment is really important. And I have looked at the single country, Germany, as an example to see what can be learned. And so again, here is the perspective. Where do the emissions occur? This time by material that is being used in Germany. And so you can see, in Germany, steel, iron and steel is also very important, and cement, and rubber and plastic. So it is sort of like the global picture. And there are differences in terms of inputs, the various inputs that cause these emissions. And the first use of materials, of course, what's interesting is that we have these imports and exports. So a lot of German production of cars and machinery goes into exports, whereas there is imported components and materials that are used in various parts of the supply chain, and the import here is basically related to where the emissions happen. It's not where the materials come from as ores, but where the emissions happen. So if an ore is imported to Germany to produce steel there, then the emissions would still be mostly in Germany, except for the mining and transport. And yeah, and you can look at where the emissions, basically, if you look at trade between sectors, you can display that as well, and that is sort of interesting. We have the construction sector here, and it is mostly used here for actually, I'm not sure why financial. I think this is the real estate sector actually that comes out really high here, whereas we have a lot of export of electrical and mechanical machinery and transport equipment that can be seen here. And you can look at these numbers in more detail. It's sort of interesting to look at. Finally, as a final quantitative investigation, I would like to talk about this paper that was published 2 weeks ago by my PhD student Kashwan Rasool. And basically, we did an index decomposition analysis where we looked at these time periods and averaged the metal use over these time periods and looked at the difference between the time periods. And we used metals. I mean, what's new here is that we actually quantified metals not only in monetary terms, but in physical terms. So we have now physical metal production extensions that we produced from British Geological Survey data. And we also did a new effort with a new data set for energy use extensions from IIOA. And then we analyzed the differences, and the aim was to look at, I was interested in the metal consumption intensity. So changes in metal consumption intensity would indicate developments in material efficiency over time. And of course, energy efficiency, and emissions intensity, so emissions per unit energy. So those are basically on the production side of the metals and the use intensity of the metals. And then we have affluency, GDP per capita developments, and developments in the population. And the interesting thing here in the first period is that we actually have a significant gain in energy efficiency, but we have a loss in terms of material efficiency. So we're using more metals per unit GDP in the later period than in the earlier period. Of course, GDP per capita increases significantly, and so does the total population. In the next period, we again see some efficiency, lower energy efficiency gains here. We surprisingly see an emissions intensity increase, and we see again a metal use intensity increase. And so in both periods, we see that GDP becomes more metals intensive than it was before in kilograms per unit GDP. And only in the third period do we see a countervailing effect of metal use per unit GDP declining. And so I find that quite striking, that we see this global development. So it seems to me from a climate mitigation perspective, materials are a big deal. They now cause close to a quarter of global greenhouse gas emissions in their production. Dematerialization or increased material efficiency is a policy goal, but it is something that only happens very recently. In previous periods, we've seen that material efficiency has actually declined, or the GDP has become more materials intensive. This could be related to the rise of investment that we have seen in rapidly industrializing countries. And investment, as I've shown, is inherently more materials intensive than other activities in the economy. So the share of investment as a share of GDP should be an important variable to look at. The picture of materials is very different from the use of energy. We see that materials are predominantly used in emerging economies in developing countries, whereas energy use is still significantly concentrated in richer countries. And what is, the hypothesis from industrial ecology is that material stocks will be built up in poorer countries. We see that, the rich countries, we have about stable steel stocks around 10 tons per capita, whereas we perceive, or our mental model is that this is something where the developing countries need to catch up in order to reach comparable standards of living. And therefore, I think it is an important question. Do we really need that large stocks? Can we build similar infrastructure with less materials? And those questions that my team has also investigated in recent years. So with that, I would like to give it back to you, Christian.
Thank you. Thank you very much, Edgar. This is a very interesting presentation, and the topic is just so important. Particularly, from also my opinion, because our economy translates to like a low carbon infrastructure, which require a huge amount of material, like renewable energies. I think that's just so crucial. It's also timely, particularly, we're also interested in this type of method. Thank you. I think, now we stop recording. Okay. So, and I wanted to start the